Hello guys, welcome back to your favorite and India's most affordable learning platform, Physics Wallah. So in the last session of work, energy, power, where we discussed the concept of conservation of mechanical energy. So when to apply this conservation of mechanical energy, and so we have solved some numericals related to the conservation of mechanical energy, right? So in continuation of the work, energy and power chapter, so we are going to deal with the lecture number 6 today. So where our major focus is going to be on, so we'll do some questions based on the conservation of mechanical energy. Then we'll study the last topic, that is the power related to this chapter. Okay, chalo. So this is going to be the last lecture of work, energy and power chapter, guys. Total 6 lectures, so every topic is covered completely. So you just have to practice so more questions to check your understanding levels, so whether you are able to do the questions on your own or not. Okay, so that's very important. So say take some DPP or practice sheet. So there are n number of free DPPs materials available in the PW app, so you can just go and check there. Okay, so like if you are unable to solve the questions, so again once revise the concepts. Okay, so as this chapter is going to be completed today, so what you do is just write the starting onwards, starting to end, all the formulas related to this chapter and the shortcuts and the tricks and the theory important points. So just write it as a short notes, so that's very important. Okay, chalo. So with very high positive energy, let's start the today's session. So that is the lecture number 6. So let's start with a very good question here. So first, so try to understand the question and try do it on your own. So what's the question says? Consider the situation in the figure. So mass of block A is m and that of block B is 2m. Okay, so this is of mass m and this is of mass 2m. Fine. So the force constant of the spring is k. So this spring has force constant k. So friction is absent everywhere. So that means there is no non-conservative force, right? So system is released from the rest. So initially the system is, so we are holding this mass. So now it is released. Okay. So with the spring unstretched, initially the spring is unstretched. So the maximum extension of the spring xm is. So that's what they are asking. So the simple question, first thing is, so can we apply the conservation of mechanical energy? Yes, sir. So here there is no friction, no non-conservative forces and no external force we are applying. Yes. So we can apply the conservation of mechanical energy in this question. So according to the conservation of mechanical energy, so the initial potential energy plus kinetic energy is equals to, so final kinetic energy plus final potential energy, ui plus ki is equals to uf plus kf. So this is a concept. Chalo. So let's understand what are the initial kinetic energy and initial potential energy and final potential energy and final kinetic energy. So this is the initial situation where the spring is unstretched. So this mass you are holding this mass. So this is the mass m. So now what I am doing is, let me consider the reference. So take this as the ground. So consider this as a ground. This is ground. Okay. Now, so try to understand. So what are all the energies that we have? So this block is on the ground, right? So the potential energy of the block B is 0 initially, and then so the spring is unstretched. So the potential energy of the spring is 0. So the potential energy of the spring is 0, and then so the potential energy of the block A, so this is at a height, so let's suppose some h. So the potential energy of the block A is h. So mgh, right? And then so here it is at rest. So the kinetic energy of the block B is 0 and kinetic energy of the block A is also 0. Yes, clear this part? Chal. Now, so come to the final scenario. So what happens? So once you release this mass, so till now you are holding this one. Sorry. So till now you are holding this. So once you release this, so what happens? So this 2m mass is more and this is m mass. So this will come down by some distance x. This will come down by some distance x. So now also this is your ground level. This is a ground level, same as of the previous one, ground. Okay, from ground, so it comes down by some x. So whenever if it comes down by x, so then what happens? So the spring elongates by x. Yes or no? So the spring will be elongated by x. So now see here, so the initial, so this will come to rest after some time. Yes or no? So the block B, it oscillates for some time and comes to rest after some time, right? So its velocity will become 0, v will become 0, and then so this is this also comes to rest after some time. So I can say that the kinetic energy of A is 0 and the kinetic energy of B block is also 0, and the potential energy of the A block, so the A block comes to this place, let's suppose, so it will be still at a height of h from the ground. So the potential energy of the A will be mgh, right? And then so the thing here it is, so the potential energy of the spring, so this time the spring is stretched, so the spring is stretched by x, so that's why the potential energy is stored in it is half kx square, because it is stretched by x distance, right? So and then so this the potential energy of the B block, so the B block has, so how it is below the ground, so below the ground means I can write minus mgh x. So how much this distance is, so below the ground it is x, so that's why its potential energy is minus mgh, right? So then apply the conservation of mechanical energy. Ui plus ki is equals to uf plus kf. So just substitute the values. So the initial potential energy, so what is the initial potential energy? So this one plus this one plus this one. So initially I could see only mgh is there, only mgh, this is 0, this is 0, this is 0, so the kinetic energy is also completely 0. And final potential energy we have minus mgx is one potential energy, and then so the other one is half kx square, and then so one more is there for A, so which is mgh. Understanding? Just I wrote everything at one place. So let me draw a line here so that you will understand easily. Yes, fine. Now so now mgh cancel, so from here, so send this x to mgx to this side, mgx is equals to half kx square. So here 1x cancel, so we need x, right? So x is equals to, sorry, this is 2 mg guys, this is 2 mg because this block mass is 2 mg, right? So this is of 2 m mass, so that's why 2 mgx, yeah, this is 2 mgx, this is 2 mgx, this is minus here and then 2 mgx. Yes, fine. Now so then see here this part, so this will come here, so x is equals to 4 mg by k. Yes or no? So this is 4 mg by k, so this is the x value. So that's it, this is the maximum elongation. Simple question. So the 4 mg by k, option 2 is the correct one, because this block is of mass 2m, so that's why the potential energy will be minus 2 mg into x. The displacement or the height from the ground is x. Clear? Understood? So any question related to conservation of mechanical energy, you just proceed this way, so then you can solve the question easily, right? Chalo. So I'll solve more questions. Let's see. So let's go for the next question. So what's the question says? See here, a child is sitting on a swing. Okay, so its minimum and maximum heights from the ground are 0.75 and 2 meters respectively. So then its maximum speed will be, see here, so this is a ceiling and here is a swing, let's suppose. So here is, this is a swing. So then, so if this swing goes to the extreme position, so this is a extreme position, so this is extreme position and this is the mean position, right? We know at extreme position the velocity will be equals to 0, and at mean position some velocity will be there. So you are sitting in a swing, so the swing is going this side, the extreme position, and again it comes back to the mean position. Here the velocity will be maximum, again it goes to the right extreme, and there the velocity will become 0, again it passes through the mean position, extreme, again mean, again extreme. So that means the SHM actually, right? So now what they are saying, so it's a minimum height and maximum height from the ground. So if I consider here is the ground, so its minimum height means at the mean position its height will be minimum. Yes or no? So when you come here to the mean position, so then the height from the ground is going to be minimum. So when you go to the extreme position, the height from the ground is going to be maximum. So that means this height is given. So this is 0.75 meters, and then this height is also given. What is this height? Which is 2 meters. Alright. So then there are no external forces acting, and there is no air drag or friction. There is no air drag or friction. You can apply the conservation of mechanical energy. So simply, shall I say the initial potential energy plus initial kinetic energy is equals to final potential energy plus final kinetic energy, right? So what are the initial? See here. So the initial potential energy will be equals to, so this is at a height of mg into 0.75, right? Initially this is at rest and this is at rest. Yes. So then or else let's write this way. So here the initial potential energy, so what is that? Mass of this. So did they give any mass? So no. So mass mg into 0.75, and then so this is the initial position initially, and then so when it goes to this side, so its kinetic energy is half mv square initially, and then so final potential energy, so when it goes to this place, so its final potential energy will be, so mg into height h is 2. So and then final kinetic energy when it goes to this place, 0. Yes or no? So I am considering this is the A or mean position, plus this is mean, this is extreme. You can write u mean plus k mean is equals to u extreme plus k extreme. You can do that way. So at the mean position, so the potential energy is there, so mg into 0.75, and the kinetic energy is also there because it has some velocity v at the mean position, so half mv square. And at the extreme position its velocity will become 0, so therefore no kinetic energy, and extreme position it is at some height 2 meters, so that's why it has potential energy m, right? Mg into 2. So now I can write this as 3/4 mg plus half mv square is equals to 2 mg. So I can cancel m. So and then this is going to be what we have to find. So the maximum speed v we have to find. So send this to that side. So we have got half v square is equals to, so 2g minus 3/4g. Yes or no? So 2g minus 3/4g. Yes. Yeah. So then half into v square is equals to, so here 4 is the LCM, so this is going to be 4g minus g. Yes or no? So 4g 0.75. So yes, so here it is 4 times, sorry, 8g. This is my bad, calculation mistake. See here, so this is 4 is the LCM, this goes 4 times, 4 into 2, 8g minus this is 3g. So from here half v square is equals to 5g by 4. Yes, fine. Now so then I can cancel, so 5 vg, this is 2 times. So here I can write, so v square is equals to 5 into g, so 5 into 10 by 2, so 5 5s are, so v square is equals to 25, v is equals to 5 meter per second. Simple calculations, that's it. So v is equals to 5 meter per second. So its velocity at the mean position is 5 meter per second. Clear guys? Understood the concept? Chal. So let's move for the next question. So what's the question says? A bob of a pendulum is released from horizontal position. So see here, so here is a bob of mass, so which is released from horizontal position. So this is initially, this is a bob of mass m, so it is released from the horizontal position. So if the length of the pendulum is 2 meters, so what is the speed with which the bob arrives at the lowermost position? See here, so consider, so this is a lowermost position, ground. So then it comes to this point, so that means I can say this is the extreme, this is the mean position, same as previous question. So assume that 10% of its energy is dissipated against the air resistance. So then find the what we have to find, speed. So when you release this one, here its initial velocity is 0. So then it comes to this point with some velocity v. Then it comes to this point with some velocity v, obviously, right? So then let's write. So let's take, this is the ground. Consider this is a ground. See, taking the reference ground is important, guys, because from there you can calculate the potential energies. So now, so this is the point A I am taking, this is the point B. We need the velocity at point B. So you know that the kinetic energy at A plus, so or else C. In the question they said that, so 10% of its energy is dissipated against the air resistance. So that means, so the final mechanical energy will be equals to 90% of the initial mechanical energy, I can say, because 10% is dissipated against the air resistance. So that means, so the final mechanical energy will be equals to, so 90 by 100 times, so the initial mechanical energy, 90 by 100 into initial mechanical energy. Again apply the same concept. Final means U final plus K final is equals to, so 90 by 100 into, so this is U initial plus K initial, right? So consider this as the initial position, this as the final position. So I can write like, so this is initially, so its kinetic energy is 0, Kf, so or else see here, sorry. So it's, yeah, correct only. So this is a 9 Uf plus Kf is equals to, so 90 by 100 times Ui plus Ki, right? So now, so this is a final position, B point. So finally its potential energy is 0, I can say. Its potential energy is 0 because it is coming to the ground, lowermost position. And its kinetic energy will be half mv square. So let its mass be m. So at its mean position or lowest position, so the velocity is v square. So which is equals to 90 by 100 times, I can write. So U initial, what is the U initial? So UI means the initial potential energy. So it is at a height of 2 meters, I can say. It is at a height of 2 meters because its length is 2 meters. When it comes to this position, so its total height will be 2 meters, right? So therefore, so mg into 2 is the initial potential energy. So and then its kinetic energy initial is equals to 0. So because it's released from the rest, it is released from a horizontal position, right? So now you can solve it easily. Half mv square is equals to 90 by 100 times, so 2 mg. So from here m cancel, so then 0 cancel, 2 ones are 2 5s are, so that we get v square is equals to, so what is there here, 5 ones are 5 2s are, so this is 18 into 2, yes or no? So this is 9 into 2 18 into, so this 2 I am sending it to that side. So v square is equals to 36. So then v is equals to 6 meter per second. V is equals to 6 meter per second. Option 2 is the correct one. Clear, guys? Sure. So now let's take one more question. So the question number 4. A uniform chain of length L is placed on a smooth horizontal table such that half of its length hangs over one edge. So it is released from the rest. So the velocity with which it leaves the table. So try to understand the question. See. So I'll draw the two scenarios here. So the initial and final. So first let's say the initial position. So this is a table. So this is a table, fine, chill. So now, so initially the chain is kept on the table in such a way that half of its length hangs like this, okay? So and then, so finally it should come to the, like it should leave the table completely. So with what velocity it leaves the table? With what velocity it leaves the table? See, try to understand the question. Just imagine. So this is the table. On the table, so what you did was, so you just took a chain. So half of it is hanging and half of it is on the table. So now you just left it. So you just hold till now you are holding. So then you released it. So then what happens? So the chain will fall down. Obviously the chain will fall down, right? So with what velocity it comes down? That's the question says. Okay. So first I am considering. So what are my ground level? So let's take. So this is the ground level. So consider this is a ground. So from ground, so what is the initial potential energy? This is the initial scenario. So this is the initial scenario and this is the final one. Okay. So then, so the initial potential energy. So from the ground, so this part is hanging. So this has mass m by 2 because the total mass of the chain be, let it be m. The total chain has mass m, right? So then here m by half of it is hanging means m by 2 is hanging, and then so this total length will be L by 2. Its total length will be L by 2. So but while considering the potential energy, so what we do, some part is touching the ground and some part is at a distance L by 2. So we consider its center of mass. To consider the height, we consider its center of mass, which is L by 4. Already we solved this kind of questions in the last class. So now I can see that, so the potential energy Ui, the initial potential energy of this chain is minus mass of the chain. So what is the hanging part? Minus m by 2 into g into height h. So what is the h? So L by 4. Yes or no? So L by 4. Why minus? Because it is below the ground. So that's why the initial potential energy is minus mgl by 8. Minus mgl by 8. So and then its initial kinetic energy is 0 because it is at rest, right? So now finally, so when it completely leaves the table, so then so the total chain will be here. So the total chain mass will be m, s, and then so its height, so some part is touching the ground and some part is at a height L. So its center of mass we take at L by 2, s. So therefore, so the final potential energy, so the UF is equals to, so minus its mass. What is the total mass? So m, right, into, so what is g only. So what is its length? So L by 2. So the final potential energy is minus mg L by 2. So now it leaves the table with some velocity v. So therefore, so the final kinetic energy will be half mv square. Half mv square is the final kinetic energy. So now you apply the conservation of mechanical energy. So what we do? So the initial kinetic energy plus initial potential energy is equals to, so final kinetic energy plus final potential energy. So what is the initial kinetic energy? 0. So initial potential energy minus mgl by 8. Minus mgl by 8. So final kinetic energy half mv square, right? So plus into minus it will be, so minus mgl by 2, this one, final potential energy. Yes. So chalo, now so let's do the calculations now. So we need what? We need the velocity v. So we need this v term. So bring everything to this side then. So what we can do? So here it is, minus mgl by 8 is equals to half mv square minus mgl by 2. So the first thing is you can cancel m in this. So then bring this gl by 2 to this side. So gl by minus gl by 8 plus gl by 2. Yes or no? Plus gl by 2. So which is equals to half v square. Half v square. So here, so 2 8 LCM. So it's going to be 8 however. So 2 1s are 2 4s are 2 into 4 8. So 8 is the LCM. Right. So from here, so this is minus gl plus, so this is going to be 4 times 4 gl, right, which is equals to half v square, right? So from here, so we get 2 1s are 2 4s are. So this is 4 gl minus gl, which is 3 gl by 4 is equals to v square. So what do we need? We need the v value. So v is equals to square root of 3gl by 4, or else you can take 4 out from the root, which is root 3gl by 2. Either root 3gl by 2 or root 3gl by 4. So the complete root is given. So take root 3gl by 4. So the velocity with which it leaves the table is root 3 GL by 4. So the same question they can give the values like the chain length is something and chain mass is something, and a mass may not give because the mass gets cancelled, and G value they ask us to take. So then you can get the, if you G and L you know, so then you can solve the numerical value also if they gave it in the question. Clear guys? Understanding? Sure. So let's go for the next question. So what's the question says? A body of mass 1 kg is thrown upwards with a velocity 20 meter per second. So this is a 1 kg block, so which is thrown upward, so with a velocity, so with an initial velocity, let's take this is the initial velocity 20 meter per second. Now so it is momentarily comes to rest after attaining a height of 18 meters. So let's suppose it reached some height 18 meters, and then so it reached this point, so where, so its mass is 1 kg, so mass will not change, it comes to rest. It comes to rest means final velocity 0. How much energy is lost due to friction? See, simple thing. So what is its initial energy? So the initial mechanical energy is equals to, so the initial kinetic energy plus initial potential energy. So let me consider this is the ground. Consider this is the ground. So initially if it is on the ground, so the initial potential energy is 0. So initially it is thrown with some velocity u, so that its initial kinetic energy will be half m u square. So half into its mass is 1 kg into, so the velocity u square, which is 20 whole square, right? So this is 400 by 2, so which is 200 joules is the initial mechanical energy. So now, so this ball has reached, so the point where it comes to rest. So then let's find the final mechanical energy. So what is the final mechanical energy? So final kinetic energy plus final potential energy. Yes. So then what is the final kinetic energy? So it comes to rest, so the final kinetic energy will become 0. Yes. So and then, so final potential energy, it attained a height of h, so mgh. So its mass is 1 kg, g value they asked us to take 10, and then h value 18 meters it attained. So that means 180 joules. So the initial mechanical energy is 200 joules and final mechanical energy is so 180 joules. So that means, so the loss in energy, the loss in energy will be equals to, so final mechanical energy minus initial mechanical energy, so which is nothing but, so initial minus final. The loss is the initial minus final. So initial is 200 joules minus final is 180 joules. So which is 20 joules is a loss in energy due to the air friction. Option 3 is 20. So 20, option D is the correct one, fourth one. Clear guys? Understood? Chal. So let's move for the next question. So what's the question says? A vertical spring with force constant K is fixed on a table. So a ball of mass m at a height h above the free upper end of the spring falls vertically on the spring, so that the spring is compressed by a distance d. So the net work done in the process is, see, try to understand the given question first. So here what they are saying is, so consider this is a ground. So there is a spring placed vertically like this, okay, and then so here is a ball of some mass m, so which is at a height h from the spring. So that's what they said. So now till this time this ball you are holding, now you just released this ball. So then after what happened, so the ball fell on the spring, so that the spring compressed. So the spring compressed, so the ball has come here, okay, ball's velocity will become 0. So this is the compression, so this is a distance d, so the spring has compressed, okay. So and then here is the ground, let me take the ground, or reference is here, from here, so this is a reference. Now try to understand the scenario. So they are asking us to find what is the work done in the process is. See, we know that the work done will be equals to the negative of the potential energy, change in potential energy. Yes or no? So work done by the conservative force or else the change in potential energy is equals to minus WC. So where the work done will be equals to minus change in potential energy, we can write. So from here the work done is equals to, so minus of, so U final minus U initial, right? So then, so the work done will be equals to, so UI minus UF. So now try to understand, so what is the, this is the initial scenario and this is the final one. So what is the initial potential energy? So initial potential energy, see here. So the initial potential energy. So ball is at the ground. So the initial potential energy of the ball is 0. So the initial potential energy of the ball is 0. Yes or no? Because the ball is on the ground now, right? So then, so the potential energy of the spring is 0 because the spring is unstretched, right? So we just need the potential energies of these two. And then after some time, so when the ball fell on this spring, so what happens? The spring compressed by the distance d. So the potential energy of the spring is there, which is half k, the compression is d, so half kd square. And so the potential energy of the so what is that, ball? So the potential energy of the ball, so this is initially on the ground, so then it is fell by, this distance is h, and again some more distance, like it is on the spring, right? So that's why I am taking this as half minus minus mg into h plus d. Why minus r? Because it is below the ground. Initially it is on the ground, so that's why its potential energy is 0. So now it is fell from here to here, so from here to here, so from here to here it is mgh, from here to here it is mgd. So total mg into h plus d, this total distance will be h plus d, right? So this, sorry, this total distance will be h plus d, right? Chal. So now I can write it here. So this is the final and this is the initial. So the total initial potential energy is 0, and then the total final potential energy will be equals to half kd square minus mg into h plus d, mg into h plus d, right? So the work done will be equals to, so the initial potential energy 0 minus, so final potential energy, which is half kd square minus mg into h plus d. So now let's multiply the minus inside here. So if you multiply the minus inside, so the work done will be equals to mg into h plus d, mg into h plus d minus half kd square, mg into h plus d half kd square. So this is the work done. Clear? So check the options. So mg into h plus d minus half kd square, mg into h plus d, the first option itself, mg into h plus d minus half kd square. Here h minus d is there, here h plus d, but plus kd square is there. So here h plus d is there, so and plus half kd square. So these two options are given same, but no, we already got the correct option in option 1. Clear guys? Chal. So let's move further, the next concept. So this is all about the work energy, the work and energy part, and we have seen, so the conservation of mechanical energy. Hope the conservation of mechanical energy concept is clear, right? So just when to apply the conservation of mechanical energy, when there are no external forces and non-conservative forces, so then the work is done only by the conservative forces. So you can apply the internal conservative forces, then you can apply the conservation of mechanical energy. So now let's go for the last topic, that is, so power. What is the power? So you know that power is the rate of energy transfer or rate of work done, right? So it's a work done by time, work done by time. Rate means per time, so it's a rate of work done, doing work. So work done by time, or we can also write it is also the rate of energy transfer. So according to the work energy theorem, we know that, so whatever the work done will be equals to the energy supplied. So that's a energy transfer by time taken. And so you already studied in the grade 10th. So the whatever the work energy supplied will be equals to the work done will be equals to the heat. So here it is not required. In thermodynamics we'll study about it. So it's heat per time. So work, energy and heat. So we can write, so the power is equals to W by T, right? So here, so what are the units? So the units are going to be, so work, which is joule per, so time, second, joule per second. So now I want you to write, so the dimensional formula for this. So write the dimensional formula. We already studied the dimensional formula in detail, right? So take the dimensional formula as a homework. So consider this as a homework 1. Okay, and this joule per second is also called watt. So the power is measured in watt, so W, right? So this is a watt, and then so that's heat by time. Clear this part, guys? Everyone? Chalo. So let's move further. So then what is the average power? So what is the average power? So power is a scalar quantity, and the SI unit of power is watt. So the SI unit of the power is watt. So and then so other unit is horsepower, 1 HP, which is 746 watts, another unit. So remember, kilowatt hour is a unit of energy, not the power. So kilowatt hour is a unit of energy, it's not the power. So 1 kilowatt hour is equals to, so we can write 3.6 into 10 to the power 6 joules. So 3.6 into 10 to the power 6 joules, 1 kilowatt hour is equals to, and 1 horsepower is equals to 746 watts. So sometimes they may give it in the questions, so just have the knowledge, guys. Clear? Chalo. So let's solve some questions related to the power. So what's the concept? Concept says a machine gun fires 240 bullets per minute. So here is a machine gun, so which fires, so 240 bullets per minute, right? So if the mass of each bullet is 10 grams and its velocity is 600 meter per second, so find the power. See, so I can write, so the power is equals to, so energy transfer by time. Simply it's a energy transfer by time. So here what is the energy transfer? So once the bullet is released from the ground gun, so it will possess the kinetic energy, right? So each bullet will possess the kinetic energy of half mv square, right? So there are total how many bullets? Total 240 bullets. So 240 bullets into half into mass of each bullet is 10 grams. So I am writing 10 by 1000 into, so velocity. So what is the velocity? 600. V square means 600 into 600 by the time taken. So see here, per minute they said, convert it to second. So by 60, because this is in meter per second, right? So convert this minute to second time, right? So then what do we get? So here two zeros gets cancelled, 1 0, so and 1 0 gets cancelled. So and then 2 1s are 2 12s are, right? So and what else is left? So here 0 cancel and 6 1s are 6 hundreds are, so 600 into 12, so which is 7200, right? So this is the power, so watts. So 7200, or which we can also write 7.2 kilowatts. Simple question. Option 2 is the correct one, guys. Understood? Chal. So let's move further. See here, a pump can take out 7200 kg of water per hour from a well 100 meters deep. So calculate the power of the pump assuming that its efficiency is 50%. See here, so simple question. So first, so there is a well, so here, so from 100 meters deep, so the water is being dug out. So now so per hour 7200 kg of water is being dug out. So then what is the power of the pump? See here, so first let's find, so the power output. So let's find, so the power output. See here, the potential energy is being used, so the energy is transferred by time. So here what kind of energy? The water is being so dug out from the well, so some height or some depth 100 meters. So mgh by time taken, right? Energy by time taken, energy transfer by time taken. So what is the mass? 7200 into g10 from how much height? So 100 meters. So and then time is per hour, so convert it to seconds, so 3000 600, right? So here it 2 times, so 2 into 10, 20, 20 into 100, 2000. So 2000 watts. So this is going to be 2 kilowatts we can write. So this is a power output, but they are asking what is the power of the pump, which is nothing but power input. So and efficiency is given. So the efficiency formula neta is equals to the power output by power input into 100, right? So from here, so we have got, so the neta is 50, power output 2 kilowatts by power input, because all the options are given in kilowatts. Let's take the power output in kilowatt itself. So then 100. So from here pi is equals to, so 2 by 50 into 100. So this is 2 times 2 into 2, 4 kilowatts. So the power input, this is the power of the pump. So the input is the power of the pump and output is this one, right? So and efficiency is 50%. Input to output, it's half, right? So the efficiency is 50%, guys. Clear? Chal, simple question. So let's move further. Let's take one more question. So what's the question says? Water falls from a height 60 meters at the rate of 15 kg per second. So to operate a turbine, so here is a turbine. So now water is falling from, so here at a height of 60 meters like this. So 60 meters height. So at a rate of 15 kg per second. Fine. Now, so the losses due to frictional forces are 10% of the energy. So 10% of the energy. How much power is generated by the turbine? So shall I say that the power generated by the turbine will be equals to 90% of the power input. 90% of the power input. Yes or no? So why? Because 10% has been lost, so due to the frictional forces, right? So that's why, so I can write here 90% means 90 by 100, so into, so what kind of energy, so of output, so total, so what kind of power is there? So here power is nothing but energy transfer by time. So energy, as the water is falling on the turbine, so I can say the potential energy mgh, so by time taken. So same concept again. So 90 by 100 into mass is 15, g is 10, in the question they said 10, and then h is 60 meters, time is per second 1, right? So here two zeros gets cancelled. So this is 90 into 90, so 8100, so which is nothing but, so I can write 8.1 kilowatts. In kilowatts they gave, so that's why 8.1 kilowatts. Simple question again, right? So let's move further. So let's take the next question, guys. So what's the question says? How much water a pump of 2 kilowatt can raise in 1 minute to a height of 10 meters? So how much water a pump of 2 kilowatts, power is given, so which is equals to, so it can raise in 1 minute. So that means, so if it is raised, what energy will be stored? The potential energy. Yes or no? So then power is given, so 2 kilowatts. So let's write 2 kilowatts. Mass, how much is the mass? So how much water we have to find? Mass into g, 10, height to a height of 10 meters by time, so rise in 1 minute, so 60. So this comes out to be, so take this as 2000, which is equals to, so m into, so this is 100 by 60. So here 0 cancel, so here also 0 cancel. So m is equals to 6 into 2, 1200 kg, which is nothing but 1 kg is equals to 1 liter, we can say. So 1200 liter water can be pumped out, right? Clear? Understood, guys? Simple question again. So now let's come to the instantaneous power. See, we know that power is equals to, so the rate of work done, right? So now, so in place of power, so the let's suppose, so the very small amount of power, so dp is equals to dw by dt, right? So here I can write, so dp is equals to, so I can write here, so in place of this f dot dr, F dot dr by dt. So dp will be equals to, so I can write F dot dv. So F dot, this is dv, yes or no? So if I integrate it on either side, so then the p will be equals to F dot v, or so the power is equals to, we can write Fv cos theta, where theta is the angle between power and force and velocity, yes or no? So or else you can also write this as p is equals to F dot v. So here you can write F is equals to ma, so into v, or you can also write m into, so this is dv by dt into v. So this is a is nothing but dv by dt. So in number of ways we can write that. Clear guys? So this is a instantaneous power, which is F dot v. Clear? Understood the concept? Chalo. So now let's go for the simple question. So what's the question says here? Force is given and velocity is given. So what is the instantaneous power? We know that P is equals to F dot v. So a simple question it is. So this is 60 I cap plus 15 j cap minus 3 k cap. So dot. So 2 I cap minus 4 j cap plus 5 k cap. So you know the dot product, right? So 60 into 2. So 120. 15 into minus 4 minus 60. So minus 3 into 5 minus 15. So this is 60 minus 15. So which is 45 watts. So is a power. So which is option 2. Very simple questions these are all. Right? Chalo. So let's go for the next question. So what's the question says, see here. A body of mass 1 kg begins to move under an action of time dependent force F is given. So where I and j are unit vectors along x and y. So what power will be developed by the force at that time? So we know that power is equals to force is given. So that's why I am writing F dot v. F dot v. So but the thing is, I don't know what is v here. Force function I have, but I don't know v. So I know the mass. So shall I use this simple equation F is equals to ma from here? So the acceleration is equals to, so F by m. Acceleration is equals to F by m. So here acceleration is equals to force function we already got 2t I cap plus 3t square j cap. This is a force by mass is 1 kg. So that means we have got the acceleration which has same is equals to force. So if you know the acceleration, can we find the velocity? If you know the acceleration, can we find the velocity? So how do you find the velocity? The velocity is equals to integration of a dt. So which is integration of, in place of a, you can write 2t I cap plus 3t square j cap. So now, so we can write this as, so 2t square by 2, so plus 3t cube by 3. So 3 cancel, 2 cancel. So t square I cap plus t cube j cap is a velocity. So just substitute it here now. So we have got force. What is that? 2t I cap plus 3t square j cap. So this is the force dot. So what is the velocity function we got? T square I cap plus, so t cube j cap. Yes. So now multiply. So 2t into t square. So which is 2t cube I cap. So this is t square t to the power 3. So which is t to the power 5 j cap. That's it. So 2t cube 3 to the power 4. No. So 2t cube plus 3 to the power 5. Yes. 3t to the power 5. Option 2. So this is not and this is also not. Right. So simple question again. Basic formulas. See, all the chapters are involved here. Okay. So you should not forget the basics, guys. Understanding? So if you know the basics, then only you can solve this question. As I am explaining, this looks simple now. But if you don't get this idea, you can't solve this question, right? Understanding? Chalo. So let's move further. Let's take the next question. So what's the question says? A car of mass m starts from rest and accelerates so that the instantaneous power delivered to the car has a constant magnitude P naught. So the power, the instantaneous power P is equals to P naught. So the instantaneous velocity of this car is directly proportional to what? So they are asking instantaneous velocity. See, I know that P is equals to, so F into F dot V. So F dot V, P is equals to F dot V. So let me write, so the very small power dP is equals to M into A into, so V here, right? So then the dP is equals to, so M into, in place of A, I am writing dV by dt into, so V. Shall we write like this? So let's do one thing. So let's integrate it on either side. So we get, so the integration of dP is equals to, so the integration of mv into dv by dt, right? Or else send this before this, let's send this dt to this side. So it will become, so the dp into dt, or else you can simply keep p only, so no issue. So which is nothing but power is equals to, so p dt is equals to mv dv, mv dv. So now I can write here, so integrate either side, p dt is equals to integration of mv dv. So from here, so the power is from where to where? So let it be p dt is nothing but p into, so what is the integration of dt? So it will be t, right? So then m is a constant, so the velocity is nothing but v square by 2. So integration of v dv will be v square by 2. So now I can write, so pt is equals to mv square by 2. So we need the instantaneous velocity v, right? So from here p v square is equals to 2 p naught t. So power is nothing but p naught, right? As per the given question, p naught t by m. So from here I can write v is equals to root over 2 p naught t by m. See the simple steps I am doing, so nothing much. So we know that power is equals to F dot V. So let's suppose the force and velocity, they both are in the same direction. We can write, so Fv cos theta, so which is Fv cos 0, right? So then in place of F I am writing Ma, I am removing the vectors form, okay? So Ma cos 0, so, right? Mav cos 0, cos 0 is 1, right? So then we got velocity, this one. So velocity is proportional to what? So they are asking in terms of time. So I could see that the velocity is directly proportional to root t. Yes or no? Root t, which is nothing but velocity is directly proportional to t to the power 1 by 2. So option 2 is the correct one, guys. So it is t to the power 1 by 2. Clear? Understood, everyone? Sure. So let's move further. So let's take one more question. A particle of mass m starting from rest undergoes uniform acceleration. If the speed acquired in time t is v, so the power delivered to the particle. So the same question. So here, so the simple and same question. So they are saying a a particle of mass m starting from rest undergoes uniform acceleration. So this is a particle of mass m, so whose initial velocity is 0 and undergoes uniform acceleration a, right? So then if the speed acquired in time t is v, so after some time t, so its velocity is v, okay? So then what is its power delivered? So power in terms of velocity we required, so we can simply use p is equals to F dot v. So let's suppose you applied the force in this direction, so the body's velocity is also in this direction. So p is equals to Fv cos 0. Cos 0 value is 1. So in place of F, I am writing Ma into V. So this is 1. So I need the velocity, right? So in terms of velocity, because see here options, so they are in velocity and time. So now in place of acceleration, I can write dv by dt s into v. So bring this t to this side, dt to this side, p dt is equals to mv dv, right? So now integrate it on either side. So initially from 0 to in t seconds, here it is at t is equals to 0 it is starting, and at time t is equals to t it is reaching a velocity v, right? So p dt, which is equals to, so the integration, so from initial velocity 0, finally it is reaching a velocity v. So mv dv. So from here, so I can write, so power is constant, so the integration of t dt is t, so from 0 to t. So and m is constant, so the integration of v is v square by 2, so from 0 to v. So right, so this is going to be pt is equals to mv square by 2. So from here, power is equals to mv square by 2t. So the power delivered will be mv square by 2t, or half mv square by t, half mv square by t, half mv square by t square, half mv square by t. Option 4 is the correct one. Clear guys? Understood? Chalo. So let's move further. So let's go for the last question of today's session. A particle of mass m is driven by a machine that delivers a constant power k watts. So if the particle starts from the rest, so the force on the particle at time t is, see here, so what's they are saying, so its power is k watts. So they said the power, and a particle of mass m is driven by a machine. So and if the particle starts from rest, see here, so this is a particle of mass m, so which has started from rest. Okay, so the power is given as k, the power is given as k for this, right? So p is equals to k, let's write. So we know that power is equals to fv. So let's suppose the force is applied in this direction, the body is also moving in the same direction, so fv cos 0. Observe carefully. So p is equals to, so fv, right? So the same thing I am doing here. So from here, so let me write, so we need the force actually. So from here, so first p is equals to, in place of f, so let me write ma into v. So here p is equals to m into, so dv by dt into v. So bring this t dt to this side, p dt is equals to mv dt, dv. So just understand the procedure, same concept. So but the question is bit twisted here. So the integration of p dt, so initially let's suppose it started from t is equals to 0 seconds, and after some time t, so it's attaining some velocity v, so 0 to some velocity v, mv dv, right? So here p into, so the integration of dt is t, so here I can write mv square by 2. So this is mv square by 2. So from here, so I can get, so the velocity is equals to, so in place of power, let's write k, because they said power is equals to k, right? K watts. So kt is equals to mv square by 2, right? So from here, let me calculate what is v square here. So 2 kt by m, right? V is equals to root over 2 kt by m. So this is fine. Now check the options. We need what is the force on the particle. So we need the force on the particle. So just concentrate here guys. So we need the force. So I know that P is equals to kV, P is equals to Fv. So now I calculated what is the V value, because here there is no, see, if you want you can write the answer here itself. P is equals to Fv. If you need force, force is equals to P by V. So P means in the given question K, K by V. But K by V option is not there here. K by V option is not there. So in terms of mass, velocity, time I required. So that's why I am finding the velocity in terms of this mass and time. So sorry, I got the momentum. This is, so what is this? Wait a minute. Sorry, this question, right? Yeah. So I got the velocity in terms of power. So root over 2 kt by m. So now what I am doing is, again I am using the same expression, P is equals to Fv. So from here, P is equals to Fv, right? So from here, so I need the force. Force is equals to P by V. So in place of P, so what is P? P is equals to K by, so in place of V, so let me write root over 2 kt by m, right? So then I can write K, so into root over m by 2 kt. So let's bring this k also to the root. So m into, so k, if it comes to the root, so k square by 2 kt. So k gets cancelled, so it is root over, so mk by 2t. So this is a force. So check the options, guys. F is equals to, so t is outside, let's make t outside. In all the options t is outside, so here it is root over m into k by 2, so into t to the power minus 1 by 2. In the denominator it is t to the power 1 by 2, but if it comes to the numerator, t to the power minus 1 by 2. So root over mk by 2 into t to the power minus 1 by 2, option 1 itself, right? So that's the only option that is left. Clear, guys? So this is all about, so the work, energy and power chapter. So I recommend you to, so do some more questions. Already we solved many numericals, but still, so solve some more numericals to understand your question solving skills, like how you are able to cope up with the subject, so how you are remembering the formulas. So all these things you can evaluate yourself. So when you solve some questions, take it as a test so that you can evaluate yourself, guys. Okay, so that's it for today's session. So in tomorrow's session we'll start the new chapter. So till then, keep studying. All the very best. Bye.